right, hello everyone. Thank you so much for joining today's webinar. I'm Indranil Bavkar. I'm a field application engineer for automation and mobility business unit at Xsense by Movella. And today I'm going to be talking about some of the challenges that subsea applications face and how these challenges can be overcome using IMU, VRU, and AHRS devices. With that said, I just want to make a few notes for everyone. So in case you're wondering, the webinar will be recorded and the recording will be sent to everyone via email and also be available on the events page that you use to register for the webinar. If you have any questions, you can type your questions in the questions tab, which you can find at the lower right bottom of your screen. And all the questions will be answered at the end of the presentation. All right, just a quick introduction about Xsense by Movella. We are a leading innovator in 3D motion tracking technology since 2000 with over 180 defining patents. We have about 200 plus employees and a global presence with offices in Europe, North America's region, Asia Pacific region, and we also have a worldwide network of partners and distributors such as Farnell, Mauser, DigiKey, etc. And we are also ISO 9001 certified since 2015. Now, the automation and mobility business unit of Xsense consists of the product line with MTI, like the industrial grade, IMUs, VRUs, AHRS devices, GNSS-enabled devices. And the main application areas are outdoor mobile robots, indoor mobile robots, smart agriculture, and marine applications. Today in this webinar, we are mainly going to focus on the marine applications, and in that as well, like underwater, like that is subsea applications. Now, without GNSS and often clear sight, orienting and positioning can be challenging under the surface of the water. And this is where IMU, VRU, and AHRS solutions provide very accurate 3D orientation data with a very small form factor. If you want to learn more about these devices, you can go to movella.com/automation and mobility. Now, these are some of the applications or some of the subsea applications: remotely operated vehicles, buoys, autonomous underwater vehicles, transponders, seafloor mapping, etc. Now, before we dive into the challenges itself, I just want to go briefly over the different IMU functions that the IMU functionality basically. So the IMUs, or the basic IMUs, are the inertial measurement units, which consist of gyroscopes, accelerometers, and magnetometers. And the output that IMUs provide is just the raw calibrated data. IMUs do not have sensor fusion algorithm. Next is the vertical reference unit, which is VRU. Now, VRUs do have sensor fusion algorithm and essentially the same sensing components as an IMU. And the output is in the form of 3D orientation data, roll, pitch, and unreferenced yaw. Now, unreferenced yaw here means that the yaw is 0 when you power up a device. Then we have attitude and heading reference system, which is very similar to VRUs. The only difference is within the yaw itself. Now here, magnetometer is also used to calculate yaw, and the yaw is going to be reference to the Earth's magnetic field. Then there's GNSS inertial navigation system, which also consists of GNSS receiver and barometer, and thus also provides 3D position, velocity, and GNSS time data on top of the 3D orientation data. Then there's RTK-enabled GNSS INS devices, which just provide much more accurate position data, just centimeter level accuracy. And then we have RTK-enabled visual inertial navigation systems, which also consists of a camera, which is mainly used for the long-term dead reckoning. Now, RTK-enabled VINS devices are mainly very helpful in GNSS-denied environments, as these devices can provide long-term dead reckoning. However, in subsea applications, it is not possible to use GNSS-enabled devices, as there's no GNSS signal underwater. And that is the reason subsea applications can mainly only use IMUs, VRUs, and AHRS devices. Now, I just want to make a quick note here, and that is whenever someone speaks about IMUs is usually used as an umbrella term for all these functionalities. So it can mean IMU, VRU, AHRS, or sometimes even GNSS-enabled devices as well. With that said, let's dive into challenges in subsea environment. Now, subsea environments can be very challenging because there's no visibility underwater. There can be strong currents underwater. Also, the subsea or the underwater ocean floor is the terrain can be very difficult to navigate. And this is when IMU, AHRS, VRU devices come into picture. Now let's talk about the primary challenge that a lot of applications face, which is the incorrect or drifting yaw or errors in the yaw readings. Now, some of the reasons are magnetic interference, which can be caused by the internal or external magnetic fields and can further cause inaccuracies within the yaw readings. Now, what do I mean by internal magnetic field? Now, internal magnetic field is the magnetic field from the rover or for example, an AUV, ROV, buoy, etc., inside which the IMU is mounted. Now, this can result from the ferromagnetic material that is used inside the ROV, AUV, or the rover itself. And the external magnetic field is the magnetic field within the environment in which this rover is operating within. Another issue is biases within gyroscopes and accelerometers. Now, MEMS-based gyroscopes used in IMU, VRU, AHRS devices develop biases due to changes in their physical properties over time. And the third one is local magnetic declination. Now, the magnetic field or the magnetic field intensity on the surface of the Earth is not uniform, and it can change from region to region and over time. And this declination at different Earth locations can introduce yaw reading offsets if not accounted for. Another major challenge is the cost. Now, effective underwater positioning and navigation solutions that are often used can be very expensive, as they might require a lot of maintenance. They can be bulky at times. Also, they might even require their own infrastructure. So these are some of the major challenges in subsea environments. And in the upcoming slides, we're going to be talking about these challenges and how and what is the solution for these challenges. So let's dive into it. So the first one, the magnetic interference. Now here you can see there's a picture of an AUV, and around it is its own magnetic field. Now this is what I mean by the internal magnetic field. Now this magnetic field is because of the ferromagnetic material that is used inside this AUV itself. And this is not going to change. Basically, it's going to be the same as these ferromagnetic materials are moving with the AUV itself or the rover itself. So these kind of homogeneous magnetic fields, which are moving with the application, can be accounted for using magnetic calibration. And if you perform a magnetic calibration after installing the IMU, VRU, or AHRS sensor inside your end application unit, such as AUV or a rover, then you can compensate for these homogeneous magnetic fields. And it will then account for the magnetic field from the end application itself and give much accurate yaw data. Now on the right side, you can see a magnetic field mapper tool. Now here, essentially when you calibrate, when you perform a magnetic calibration, what you're essentially trying to do is, after installing the sensor inside the rover, you want to move the rover in 3D space whenever possible to account for all the points within the 3D space, or as many points as possible within the 3D space to give you much more robust calibration data. This is what this sphere indicates. Now you can see there are certain points on this sphere. Now when you move the rover in 3D space, you're going to see points populate inside this sphere. Now, I understand that it's not always possible to perform a 3D calibration, especially, for example, in heavy ground vehicle applications, where it's not possible to move the vehicle in a 3D space. It can only move in a 2D plane, which is the ground surface. In that case, it is also fine to just perform a 2D calibration. However, in the subsea applications, performing a 3D magnetic calibration should not be an issue at all. Here you can see the after calibration results. So basically, these are the before calibration, and this blue line is the after calibration result. Essentially, what we are looking at here is the norm data. So after an acceptable and a good magnetic calibration, you should see that your norm is very constant at around the value 1. So this is what it's representing. The next one is gyro biases. Now, MEMS-based devices, as these MEMS-based devices age, gyroscopes, accelerometers, for example, they're going to face certain changes in their physical properties, and because of that, certain biases are going to get introduced. Now here, as you can see, there's a screenshot of the angular velocity data from an IMU, VRU, or an AHRS device, which was placed stationary on a desk. Now, even though the unit was stationary, you can see that the angular velocity values are not 0. So there's a certain offset in the angular velocity values. Now, because of this offset, it can introduce a yaw offset or a inaccuracy in the yaw readings. And this is what needs to be accounted for. Now, how can this be done? So what you can do is you can use a manual gyro bias estimation or a no rotation update functionality. So what this functionality essentially does is it tells the IMU VRU AHRS device that the unit is currently stationary, and that the yaw, since the device is stationary at the moment, the yaw should be stable. And that's what is represented in this screenshot on the right side. So basically, when you send a command for manual gyro bias estimation or a no rotation update command to the sensor and tell it that for the next 5 seconds, 4 to 5 seconds, for example, the unit is going to be stationary, then it's going to tell the sensor fusion algorithm that the unit is stationary and there is no need to change the yaw. Otherwise, if this is not performed, because of these offsets and biases, you can see that the unit is going to show a drifting in the yaw values. Another cause of these biases is mechanical stress or vibrations. Now, vibrations can result from the rotating motors or propellers in the vehicle in which the sensing device is mounted on. Now, this can be mitigated using a rubber damper such as this one. So basically, when you mount the IMU device in your end application, you can use rubber dampers such as this one, which can absorb most of the vibration and shocks and avoid it from translating it directly over to the sensor. And in case of surface mountable devices, for example, Xsense MTI-1 series, instead of using hand soldering or PLCC sockets to mount your IMU device on your end application, you can use a reflow soldering process. Otherwise, hand soldering or PLCC sockets can introduce a lot of mechanical stress, which can increase the offset you can see in the angular velocity values and further introduce certain inaccuracies within your readings. Now, the next one is the local magnetic declination. Now, as you can see in these images here, the magnetic field on the surface of the Earth is not always uniform. So the intensity is going to be higher in certain regions. The magnetic field intensity is going to be lower in certain regions. And it can also change with time as well. So for example, you can see here, this is the world magnetic model for 2010. So for 2020, it's going to be different. Usually, they update it every 10 years. So what can be done in this case? So it is very crucial to have the world magnetic model embedded within the firmware of the IMU AHRS device itself, so that the end user can send the location in which the unit is going to be operating within in the form of latitude, longitude, and altitude, which can be stored on the onboard memory of the sensor. And then the device can accurately reference its yaw with respect to the local magnetic field. And depending on the location on the Earth, this can result in an offset correction of several degrees. Now, another challenge that we spoke about in the earlier slides is the high costs. Now, you can see on the right side, these are the fiber optic gyroscopes and ring laser gyroscopes. As you can see here, they're very bulky and can be very expensive, can cost in the range of upwards of $20,000 and upwards. And since these are very bulky, they're not very good when used. If you want to use these sensors inside AUVs, ROVs, for example, and can be very expensive. Now there's sonar systems which can cost tens of thousands of dollars and require a lot of maintenance. Then there's acoustic positioning systems such as LBLs, SBLs, as you can see in the picture here. And these require deployment of transponders and can be very expensive, as these kind of application environments require their own infrastructure by deploying these transponders. In this case, what is the solution? So the solution is to use MEMS-based IMU AHRS devices, which consist of 3D accelerometers, gyroscopes, and magnetometers, and are very compact and can offer a very reliable and inexpensive solution, as these devices can range just between $100 to $2,000. Now, this range, I'm talking about industrial grade IMU AHRS devices. Now, on the right side, you can see these devices can have different form factors with surface mountable devices, where the size can just be 12 mm into 12 mm and can range up to rugged encased IP67 68 rated cases, and can offer different functionalities and also support different communication protocols such as UART, USB, RS-232, RS-422, I2C, SPI, etc. Now, we have a case study that I want to share with you. It's with the Carnegie Mellon University, which is one of our customers. Now, the team at the Carnegie Mellon University developed this AUV called Tartan AUV, and they used the MTI vertical reference unit for precise underwater navigation inside this AUV. Now, these were some of the challenges that they faced before using the MTI vertical reference unit. And the challenges were drift in the dead reckoning calculations, SDK compatibility with NVIDIA Jetson platform. They needed sensor fusion and data synchronization, and the Doppler velocity log that they were using basically had a very low output rate, which was just 10 hertz. Now, the MTI vertical reference unit was able to fill in these gaps or these challenges by offering solutions such as accurate attitude and heading data. Xsense also has, we also have our own ROS1 and ROS2 drivers, which are compatible with the NVIDIA Jetson platform. And our sensor fusion algorithm is very robust and provides very accurate data. And we also provide synchronization functionality. And the VRU measurements from the MTI vertical reference unit was able to fill in the gaps between the low frequency DVL data by offering maximum output rate of up to 400 hertz. Now, if you have any questions or if you are curious about our products, you can go to knowledge base, where we have a lot of integration articles, frequently asked questions, and customers can also ask questions on our forum over there. We also have tutorial videos, which consists of informative videos on our products and features, functionalities offered, etc. If you want to talk to us directly, you can send an email to support@movella.com, where one of the field application engineers, such as myself, can contact you directly. All right, let's get to the questions now. All right, I see a question here. How is the world magnetic model stored on your devices? So the world magnetic model is embedded inside the firmware itself. So we make sure that whenever there's a firmware update, we make sure that the firmwares has the latest world magnetic model. I see another question here from Momshi. I have a small question, not only in the sea, but outside also. Do we need to calibrate the IMU compulsory? Yeah, especially if you're using an AHRS device, which provides a reference yaw, it is very important to calibrate it, perform a magnetic calibration, so that you can account for the homogeneous magnetic fields coming from your end application itself. This will take into account all the magnetic fields within your vehicle, for example, a rover that you're using. So yeah, it is highly recommended to perform a magnetic calibration. And there are multiple ways to perform a magnetic calibration too. You can use the tool, or you can also use commands from the SDK as well. Another question that I see here is which MTI is commonly used in this application? So I'm assuming the Subsea applications. Mainly, I've seen customers use AHRS devices since it provides reference yaw, which is a reference to the Earth's magnetic field, so it can provide true north heading, and it can be surface mountable, so basically from MTI 1 series, which is MTI 3, or it can be MTI 630, MTI 300, and based on what kind of form factor you're looking for, and what kind of accuracy you're looking for, and also which communication protocol you're looking for, you can use different MTI products. I see a question here from Stefan. So on slide 11, you argue for using IMU over acoustic reference systems. How do you solve drift compensation without an absolute reference? So it's definitely not one or the other. It's basically if you want a low-cost solution, low-cost and accurate solution for underwater navigation, stabilization, you can use MEMS-based IMUs, basically. However, for certain applications which require very high accuracy and also are completely fine with the costs that are associated with, for example, acoustic reference systems, in those kind of applications, you can certainly use the acoustic reference systems in addition to the IMUs. However, customers looking for the low-cost solutions can go for just the MEMS-based IMUs. I have another question from, can the lat long be updated to the device through the ROS package? Yes, you can update the location of the sensor, basically the lat long, using the package itself, the ROS package, or you can use our SDK commands as well. I have another question from Vamshi, and it's, can't we store the calibration in NV memory and use further? So once you perform a magnetic calibration, there's an option that you can write the new calibration data into the memory itself, memory of the device, and after which it will account for the new magnetic calibration values. You can also see the new calibration values inside the modeling parameters in our MT Manager application. Another question I have here is, how can one integrate the IMU into their application? So here at Xsense, we make it very easy to integrate the devices by offering our MT software suite, which has our graphical user interface MT Manager software, where you can literally visualize the data, also change the output settings, or even the device settings, and also record the data as well. And it also consists of the software development kit, where we offer example codes in different coding platforms such as C++, C#, Python. We also have ROS1, ROS2 libraries as well, and all of our our entire portfolio also consists of different communication protocols, or products that support different communication protocols. So it's very easy to integrate our products like IMUs, VRUs, AHRS, for example, into your applications. So another question that I have is about world magnetic model. You implement world magnetic model equations in your device and update it every 5 or 7 years with some software update tool. Yeah, so basically we include or implement the world magnetic model within the firmware itself. And yes, whenever there is an update in the world magnetic model, it is included within the firmware update itself as well. So once you install the new firmware, if there is an update in the world magnetic model, it will include that. Another question that I have here is, if we see the magnetic calibration changes rapidly, what is the process available to follow to avoid the inaccuracy of magnetometer accuracy? So the magnetic calibration is mainly or should mainly be used with the to account for the magnetic calibration from the end application unit itself, like the rover. If your environment within which you're operating in, which has a lot of external magnetic fields or inhomogeneous magnetic fields within that environment, those magnetic fields cannot be accounted for using magnetic calibration. In that case, it is better to use a vertical reference unit, which provides unreferenced yaw, where it does not make use of the magnetometer for the yaw readings. The yaw will start at 0 when you power up the device. All right, I have another question here. Is it possible to use one sensor to inform the calibration of another? Say use the gyro data to inform the magnetometer calibration. I'm sorry, I don't think I completely understand the question. Possible to use one sensor to inform the calibration of another. Say use the gyro data to inform the magnetometer calibration. So all of our sensors are calibrated in our facility, production facility in the Netherlands, and they are also they undergo a very precise calibration process. And you can find these calibration values for gyroscopes, accelerometers, and magnetometers inside the modeling parameters in MT Manager software. However, these calibration values are specific to those sensing components, basically. So gyroscopes, accelerometers, and magnetometers. Another question is, working with MTI3, it turns out that working in tight spaces, as in AUV applications, heading is not unusable due to electric interference. Is there a solution to overcome? Yeah, with electrical interference, for example, high power cables. So we usually recommend to mount the MTI devices at least a little bit away from the high power cables, for example, about 10 to 15 centimeters at least, and also on top of that perform magnetic calibration. I have another question here. If fusing the AHRS info with other sensors, like a DVL for subsea application, what is the recommended fusion method or filter structure? Example, EK, extended Kalman filter, or UKF, or something else. So we have our proprietary sensor fusion algorithm, and that is only that can only work within our devices. And for synchronization with other sensors such as DVL, cameras, etc., we offer synchronization functionality. So and there are multiple synchronization functions that you can use. I have an article which, if you go to our knowledge base and type synchronization with MTI devices, you can find an article which talks about all the synchronization functions that the MTI devices offer, and also examples of how you can synchronize other devices with MTI as well. How do you cope with lateral acceleration when using VRU? Any experience integrating with speed sensors like in airplanes? So VRU devices, for example, we usually, for example, for positioning, like within our sensor fusion algorithm itself, we do not offer the positioning for through VRU AHRS devices. But there are certain calculations that you can do on your end. We have an article on that as well on our knowledge base, which talks about how you can find the relative position data or velocity data from the acceleration data itself. All right, I think those were all the questions here. If you have any other questions, or if the answers that I provided weren't clear, please make sure or feel free to reach out to support@movella.com, where one of our field application engineers can help you with your questions as well. All right, thank you so much for joining, everyone, and have a wonderful day.